Hello, this is mlcourse.ai, lecture 4, linear models. This talking head is Yuri or Yorko, and let's visit mlcourse.ai main site, and we see that topic 4 is actually really very huge. So there are 4 parts, or even 5 parts. So it starts with linear classification and regression, then logistic regression, regularization, and so on. So at this point, there will be slight difference between these video lectures and the material itself. So we see that topic 4 is this huge about linear models, and then topic 6 is about feature engineering and feature selection. So actually lecture 6 will be about regression, so this first part. So we'll remember supervised learning includes classification and regression as 2 particular general tasks. And first we'll do with classification, and only that we'll go for regression. But we encourage you to read topic 4 about feature engineering and feature selection. We'll actually be doing that in our Kaggle in-class competitions, and assignments 4 and assignments 6 are devoted to beating baselines in these Kaggle in-class competitions. So for this lecture 4, we'll deal with logistic regression, so this second part. We'll first cover some math, so we'll be going through this material and I'll be drawing some formulas, some pictures explaining this material. And then in the second part of this lecture we'll write some code, and we'll go for Kaggle in-class competition about Alice, about user identification by tracking websites, and we'll beat simple baselines in this competition. So let's go. Logistic regression is a type of a linear classifier. So if we take a look at this picture, we'd like to separate these points into 2 classes by a really simple decision boundary, by a hyperplane. So the idea is that we've got several features and we can visualize our data in some d-dimensional space. So let's just draw some Cartesian space. So these are our features, x1, x2, x3, and so on. These might be really some simple features like age, gender. So gender is binary, not so interesting in this case. Maybe salary, maybe x3 is number of children, and so on. So actually we've got more features than just 3. Let's say we've got d features, so d is the number of dimensions. And at this point we come to some difficulties that we can't actually visualize a d-dimensional space for d more than 3. So even 4 dimensions can be visualized by our brain, but still we can kind of make this mental trick and just suppose we can understand this d-dimensional space just as an extension of 2 dimensions and 3 dimensions. There is a popular phrase by Jeffrey Hinton about that. So how can you visualize 14-dimensional space? Just draw a picture like this, 3 dimensions, and confidently say 14, and this will be your 14-dimensional space. Okay, so the idea is that by drawing such pictures we can sort of understand what's going on in a d-dimensional space. Okay, and in this d-dimensional space we'll have some, let's say, some classes, positive objects, maybe people who churned or people who didn't churn. Just to keep it simple, let's think that we've got some positive examples and some negative examples. They can intermingle, so some minuses can be here in the cloud of pluses, positive examples. And we'd like to separate these objects with some simple decision boundary, let's say with a hyperplane. So this will be a hyperplane separating these 2 classes. So even simpler, for 2 dimensions, this will be just a line. Yep, so if we've got 2 dimensions, x1 and x2, our points will be separated just with a line. In 3 dimensions, this will be a plane, So in d dimensions, this will be a d-1 dimensional hyperplane. Okay, and so in general, a hyperplane can be described by an equation W transposed x equals 0. So let's go into it. So if we switch back to our material, we'll see that a linear classifier will be described by an equation sine of this W transposed x. So let's dig into it. What does it mean? I'll start with an equation of a line. So from school we're familiar with a really simple expression that if we've got y-axis and x-axis, a line can be described with a really simple expression, y equals k multiplied by x and plus b. So actually the equation W transposed x equals 0 is only a generalization. So let's show that this is a special case. We'll do only a simple refactoring. So instead of y, we'll write x2, and instead of x, we'll write x1. And so we'll see, so let's here substitute x1 and x2. And so in this case, the equation will be x2 equals kx1 plus b. What I'm doing right now, I'll deliver you geometric intuition about linear classifier, and from that we'll go for logistic regression as a particular case. Okay, so here we've got an equation for x2 and xy, and let's see that actually this can be transformed into k x1 minus x2 plus b equals 0. And you see it's pretty much the same as W transposed x equals 0. Okay, so for now I'll put arrows here to describe that these are vectors, but further I'll be omitting these. So these are vectors actually. And you see it's pretty much the same if we set W to be equal to a vector k, and then minus 1, and then b. It's better to make b the first component, sorry. So b, then k, then minus 1. And if we set a vector of x as being 1, then x1 and then x2, so this is pretty much the same. If we do inner product between these vectors, W transposed x, we'll see that this will be b, so b multiplied by 1, then plus k multiplied by x1, and then minus 2 multiplied by x2, and we've got this expression. So a simple line described by an equation y equals kx plus b, what we know from school, it's a special case of an equation W transposed x equals 0. And then if we go to higher dimensions, we've got W transposed x equals 0. So it will describe a hyperplane W0 plus W1 x1 plus and so on, WD xd equals 0. Okay, so it's actually an equation for a d-dimensional hyperplane. How does it help here? I'll start again from scratch. So we've got space, we've got a hyperplane, and this hyperplane separates pluses and minuses, positive and negative examples in our classification task. So on this hyperplane, we've got an equation W transposed x equals 0. So actually this hyperplane separates space into two regions where this equation is, where this expression W transposed x is positive or negative. So, and again, it's even simpler to draw it in 2D. So we've got a line. The equation here is double transposed x equals 0. And in one semi-space, in one part of the space, this expression double transposed x is greater than 0. And in another part, it's going to be negative. Double transposed x is less than 0. Okay, and where it's positive, we'll predict class 1. So these are our pluses. Here are our minuses. So for new objects, we'll predict a label according to the expression double transposed x. We can make mistakes sometimes, so some minuses can be here, some pluses can be here, so our classification won't be ideal. But the idea is that if we have a new test object, let's draw it as a question mark. So we've got a new point in our space, and we'll calculate double transposed x and make a prediction correspondingly. What's the idea behind that? So actually the geometric intuition is that double transposed x is a distance from a point to a hyperplane. So if we solve this task, so it's from analytical geometry. So if we have a hyperplane double transposed x equals 0, so what's the distance from some point described with vector xa to this hyperplane? So this distance, let's call it rho. So what's the expression for rho? So I'm omitting here details, but I strongly encourage you to derive it yourself. But the idea is that rho x is proportional to exactly doubly transposed xa. We only need to divide by the norm of vector w here. This is L2 norm. So L2 norm is actually a very simple thing. It's all components of vector w, w0 squared plus w1 squared, and so on, plus wd squared, and then square root from all of this. Okay, so this is the expression for rho, and we are only interested in that rho, this distance from a point to a hyperplane, is proportional to exactly this expression doubly transposed xa. Well, so this rho is can actually be any real number, so it can be positive and negative. And for different points in our space, this rho is positive and negative, and according to the sign of actually this distance, we are doing classification. So for this test object that was orange, let's call it again xa, so point A with a vector xa. So we calculate this distance from point A to hyperplane, this rho. So it's going to be proportional to double transposed xa, and then we are interested whether this distance is positive or negative. So actually our classification will be done by taking a look at the sign of this distance. So typically the answer of a classifier, so we'll have a classifier, and for any vector x, it's going to return some answer. So typically it's denoted by a for answer, and an answer or a prediction for some point xa. In this case will be the sign of this distance. So we first calculate double transposed xa, and a geometric intuition is that it's a distance to a hyperplane. Only that. So it's actually the same distance as we think intuitively, only with one difference, that it can be positive or negative depending on whether the point is on one side from hyperplane or from another. Okay, so we've calculated it, and now we only take a look at the sign of this expression, and this is our answer. So this guy is either -1 or 1 or +1. Okay, and here we need to agree that in our binary classification, labels are either -1 or 1. So sometimes there might be a confusion here because sometimes y's are actually 0s and 1s. But here we'll stick to this designation, so it will be a bit more convenient to use -1 and +1. Okay, so this is actually, so this classifier is a linear classifier. Okay, and we return to the main material. We see it here. So that the answer on object on an instance x is the sign of expression W transposed x. Okay, and now we see the intuition behind that. Geometrically, we'll have a hyperplane, and depending on the signed distance from a point to this hyperplane, we return either +1 or -1. So really simple, this is a linear classifier. So logistic regression will be separate as a particular case of a linear classifier, but we actually don't want to predict just -1 or +1, or either a client is going to be good or bad, churned or loyal. So actually we are also interested in probabilities. So a really nice property of logistic regression will be its ability to predict probabilities of certain events. And some motivation why this can be helpful. So suppose we are solving a task of predicting default probability. So we've got some bank clients, we've collected some history, and we know that some clients with certain features didn't return money, but others returned it in time. And based on some features, we can predict either a client is going to be good or bad, but suppose we can also predict the probability of default. So in that case, we can make such rating. So it's called a scoring card. And we've got some clients, Mike, Jack, Larry, Kate, and so on. And we can actually sort these predictions by this default probability. So Mike is going to be really, so we are going to predict that Mike is going to be bad, so he's not going to return money, almost 0.8 probability of default. And it's really helpful to have such rating because we can tune some threshold, like here 15%. And for those guys who've got predicted probability higher than 15%, we'll go into refuse loan to them, so this will be denial. And other guys with predicted probability lower than 15%, we predicted these are good, and we grant them a loan. Okay, so this special value of 15%, it's arbitrary, and it can be tuned depending on the bank's politics. But here the idea is that we have some intuition whether the model is confident in the prediction or not. So, okay, so for Mike, the model is pretty sure that Mike is not going to return money. But for Jessica, the model says that, well, Jessica is most probably going to be a good client, and we can grant her a loan. It's much better to have some degree of confidence from a model, so not just zeros and ones or -1s and +1s, but still some degree of certainty. And so actually with predicting default, it's even more better to have predicted probabilities, because we can multiply these predicted probabilities by the amount granted, and we can thus estimate actually the expectation of losses. Okay, so in many scenarios, it's much better to have predicted probabilities instead of just labels. And logistic regression is especially good for predicting probabilities. Okay, let's think about it, how we can predict probabilities of class 1 if we again stick to linear classifier. Okay, so suppose we can do that. We can separate points with a hyperplane. So we can build actually a function W transposed X. And so it's going to be some real number. And we've covered its intuition. It's just a distance to hyperplane. One more remark here. So typically we'll have vector x with our features. So this will be feature x1, x2, and so on, d. But we'll also add feature 1. So by definition, it's equal to 1. This will be x0. So it will be convenient just to write W transposed x. Otherwise, we'll have to write W transposed x plus some separate coefficient W0. So we don't want to write this each time. In this notation, we'll just have W0 right here in this inner product. So our vector W will be again W0 and so on, WD. So this will be much nicer to write just W transposed x without having to sum it with W0. Okay, so we'll further dive into the process how we get actually this vector of weights. But for now, just suppose we've got this vector of weights. In a real world task, these x features will be again something like age, salary, and so on. And maybe xd is something like debt, if a client has a debt. And our model will learn separate coefficients for each of these features. So we'll account for age with some coefficient, so we'll multiply it by W1, we'll multiply salary by W2, and so on. We'll multiply debt by WD. The most interesting part, of course, is going to be how we are going to know that age shall be multiplied by some WH or W1. So salary will be multiplied by W salary. Okay, these will be just concrete numbers. Let's say 1.7 or minus 0.2. How we come up to it, we'll cover later. But for now, we can multiply the vector of client features by a vector of weights, and we get a real number. So it can be from minus infinity to plus infinity. What if we'd like to predict probability of class 1? We'll designate it like this, P plus. So actually it will be conditioned probability that y equals plus 1 if we have, if we observe a vector x of features. Okay, so actually it's a probability, so definitely it should be in this interval from 0 to 1, including borders, including 0 and 1. So how can we make such a prediction if our W transposed x is actually a real number? Okay, so first step to do is that from predicted probabilities we can simply switch to predicted ratios. Odds ratio will be by definition P plus divided by P minus. It's a really simple thing. So let's say we've got just a small detour explaining this odds ratio. So I really like football, and if I see Real Madrid playing with, let's say, Manchester United, let's say I've got 3-to-1 odds for Real Madrid actually winning. And from these odds, we can easily go to predicted probabilities. So it's actually 0.6 probability that Real is going to win, and 0.4 probability that Manchester is going to win. Okay, I actually support Manchester United, but just for this example. Okay, so odds ratio for class plus 1 is going to be predicted probability of class 1 divided by predicted probability of class minus. And here we'll stick to a simple case of just binary classification. So this expression is going to be p plus divided by 1 minus p plus, because we've got only two variants. Either we predict class plus 1 or class minus 1. So these probabilities shall definitely sum up to 1. Okay, so actually this odds ratio will be now laying in this interval from 0 to plus infinity, or the same as r plus. So these are going to be non-negative numbers. Okay, and now what we actually would like to do, we'd like to somehow map these distances, the doubly transposed x. We know that this stands for distance to hyperplane. We just think of how can we map it to predicted probabilities. So how can we actually make predictions of this thing p plus class 1 probability with this linear model. So actually if we can calculate the distance to hyperplane. Okay, and the last trick is to go from this odds ratio to its logarithm. Logarithm of this odds ratio now will be actually just a real number. Okay, so if odds ratio is a non-negative, then we can calculate its logarithm. It's going to be a real number. Okay, there might be some problems if odds ratio is equal to 0. So if predicted probability is just 0, so then we'll have logarithm of 0. But if we just define that like logarithm of 0 is minus infinity, then it's okay. Okay, so why do we actually need this logarithm? Because now the main idea of logistic regression will be predicting this logarithm of odds ratio for class plus 1 just with a linear function with doubly transposed x. Okay? So here we'll have predicted probability for class plus 1. So this is going to be p plus divided over 1 minus p plus. And if I put equality sign here, I'll also specify that it's going to be a prediction. So this hat stands for prediction of logistic regression. And so now it's everything is all right. So on the left side we've got a real number, and on the right side we also have a real number. So it means that with a linear model with this doubly transposed x, we can predict logarithm of odds for positive classification. That's the main idea. And from here we can derive p plus. So if we've got an equation that logarithm of this expression equals to double transposed x, we can easily derive, or maybe not so easily, but after some work, we can derive that p plus is going to be expressed with the very same expression. So first we do exponentiation. So it's e to the power of doubly transposed x, and then divided over 1 plus the same expression, e to doubly transposed x. And it's a common practice to divide here in numerator and denominator by the very same expression, e to doubly transposed x, to get 1 divided over 1 plus e to the power minus doubly transposed x. And so this function is really popular. So if we designate this argument just by z, so this function is called a sigmoid function. So a sigmoid function of some argument z is 1 divided over 1 plus e to minus z. And so we have that logistic regression actually predicts this probability p plus with sigmoid of doubly transposed x. Okay, let's analyze a bit this sigmoid function. Let's return to course material and see, this is here, this is sigmoid function, this is pretty much the very same derivation, and we got p plus equals to sigmoid of doubly transposed x. Let's dive a bit deeper into it, so what it actually means. So a sigmoid function will look like this. So sigmoid of z, 1 over 1 plus e2 minus z. Let's just analyze it a bit. What if z goes to plus infinity? Then the denominator will be really close to 1. Yep, so e2 minus z, if z is plus infinity, will converge to 0. And so putting it mathematically correctly, if z limit tends to plus infinity, sigmoid will be 1, right? This limit is plus 1. So z is really, really high, e2 minus z will be really, really low, and so this will be 1 divided by 1, so just 1. And by the same token, if z approaches minus infinity, what it's going to be? If z is minus infinity, then this expression is really very, very big. It approaches plus infinity, and we divide 1 by a really large value. So this limit will be going to be 0. Okay, so a bit of mathematical notation from calculus. So this, let's analyze it a bit. So we've got 1 here. So the limit will be 1, but it will approach it from here, from the downside. So actually this limit will be 1 minus 0. It's designated like this, meaning that the function sigmoid of z will be approaching 1 from here. Yep. And the same for the second limit. This limit will be 0 plus 0. It means that the values of sigmoid function are still positive, and here when z is really approaching minus infinity, it will behave like this. Okay, and a bit of more analysis. When z is equal to 0, then e2 minus 0 will be 1, and the expression will be equal to 1/2. 1/2 here when z is equal to 0. So this is z, this is sigmoid of z. Okay, and so it looks something like this. Okay, all this picture. So here is sigmoid function. So what actually logistic regression does is it calculates doubly transposed x, then exponentiates it with minus, and then converts to sigmoid function 1 over 1 plus this expression. Or simpler, just it calculates doubly transposed x and applies sigmoid function to this expression. What it means is that logistic regression calculates this expression z, so it's equals to doubly transposed x. We calculate this inner product, and if it's very high, let's say 10, then the value of sigmoid will be close to 1. And contrary, if z is some low value, like minus 20, then we'll calculate this expression, and it's going to be something close to 0. And for large values of this inner product W transposed X, we'll have predicted values close to 1, and for low values, something really close to 0. So that's the main idea. And if we still would like to make a binary decision, like with credit scoring, so either we grant client a loan or refuse, so we'll put some threshold like this, let's say 0.15, and so here we make binary decision. If this predicted probability is higher, then we refuse, so then we predict class 1, otherwise we predict class -1. Okay, so here it is, the very same derivation, just a bit more details about that. So it's actually how logistic regression works for prediction. So when we already have these W's, that's how it works. And to specify even more, we'll have some specific coefficient for salary. So here in this inner product, we'll have some term like W for salary multiplied by feature salary. And if we have a rich client, let's say salary is equal to something large, let's say salary is 10 to the power of 6, I don't know, boxes per year, or maybe 5 multiplied by 10 to the power of 6. Okay, if we have some coefficient for salary, let's say it's positive 1.5, so this will this term is going to be really large, and it makes a really large contribution to this final inner product W transposed X. And so if salary is high, this moves this point closer to the right, and so then predicted probability is going to be high. Okay, sorry, for this example I'll change it to a negative coefficient, because if a client is rich, we're not going to predict that he's going to be a bad client, not returning debts. Okay, so we'll make this coefficient negative, and if salary is high, this will move point to the left, and so the predicted probability of default will be lower. And the higher is the salary, the lower the predicted probability is going to be. Okay, I'll just write that at this point there is some instance, some observation or client with a high salary, something like 5 multiplied by 10 to the power of 6. But on the contrary, if salary is really low, that would mean that with negative coefficient W salary, this will make this inner product larger, and this will move the point here to the right, and predicted probability will be higher. So at this point, let's say there will be a guy with salary something like 4 and 10 to the power of 4. So if salary is much lower, then the predicted probability is going to be higher. Okay, so in a nutshell, that's how it works for prediction. And the trickiest part is actually how we learn this vector of coefficients W. So for now it was about prediction, but now the main question is, how do we get these W's? We need some really nice technique to learn all these coefficients, W0 and so on, up to WD. Its a second part is about maximal likelihood estimation and logistic regression. So I'll shortly skip through it and explain you how we actually can learn these coefficients W through an optimization procedure, and it has really nice probabilistic foundations. So logistic regression is theoretically very well studied, and here I stick to machine learning view on logistic regression. So we'll actually convert this problem of finding nice coefficients W, so we'll actually convert it into an optimization task. So the very same approach will be valid for really complex models, some very frightening neural nets. So typically it goes with a problem formulation, and then the final step is optimization. So it's really a foundation for understanding neural nets. Okay, so in case of logistic regression, we'll have really nice motivation for that. We'll cover this MLE approach, maximum, likelihood, estimation. So it's a very well-known procedure in statistics. I'll describe it really intuitively. Maybe I'm putting it too simply and I'm not strict enough. But the idea is that if you have several hypotheses for describing some observation, you just stick to the most probable, so the explanation, the hypothesis, which is the most likely, which has the highest probability. So just for instance, if you are passing by a shop and you see that it's closed, it's your observation. So you see that a shop is closed, and you'd like to somehow explain it to yourself, and maybe you've got two hypotheses. So let's say the first hypothesis is that I'll draw a small picture for that. So we see a shop and it's closed, and maybe we were passing by this shop at March 17 at 9 p.m. Okay, and maybe we've got two hypotheses. Actually, we have infinitely many hypotheses, but let's say that we consider two explanations of why this shop is closed. So hypothesis one will be that the shop is closed once per year, and it's done on March 17, so that on March 17 it's closed every year. And just by chance we were passing by on March 17, and that's why it closed. Okay, and maybe hypothesis 2 is that the shop is open till 7 p.m. and so just at 9 p.m. it's closed. Okay, so this explanation is not mathematical at all, but somehow in our brain we just weight these two hypotheses, and we would definitely stick to the second one as being more probable. So our explanation to ourselves will be that, of course, okay, so it's 9 p.m. too late, and that's why the shop is closed. So pretty much the same approach works for statistics, for picking a hypothesis that explains our observations in a most probable way. So maximal likelihood principle is very often used in statistics to fit distributions to observed data. So let's say we've got a bunch of people and we measured their height, and we plot the distribution of these heights. So we see 182 centimeters, 179, 162, 205, 202, 182. So actually we have a vector of our observations. Just let's call it just one feature, height. And in statistics we are typically interested in empirical distributions and fitting actually parametric distributions to this observed data. So for our distribution of weights, we can plot a histogram like this. So we just split H into several bins, let's say of 10 centimeters, and we plot a histogram of our observations. And just like in pandas, if you build a histogram and then you fit some distribution here, just by the same token, you can pick normal distribution, let's say, and find its parameters for which the observed vector of height is most probable. Okay, so normal distribution has two parameters, mean value and standard deviation, and we can actually estimate these parameters just from our distribution. Okay, so this can be done in statistics very strictly, very mathematically. So here we made an assumption that height is distributed normally. So actually it's a very nice assumption. If we have thousands of observations, we'll see that it's really distributed very closely to normally. And with data, we can actually estimate this distribution. We can estimate mu, so mean and standard deviation from our data. And actually, the estimate for mu can be is really intuitive. It's just average of the values in our vector. Okay, so if it's x, let's call it a vector of height, just h. So we sum all heights, and just divide by the number of our observations. Okay, so this can be done strictly. It's a very well-known statistical procedure, but I would say that here we apply max likelihood estimation just to estimate our parameters of our model if we have observations. Well, so pretty much the same idea. With logistic regression, we'll estimate W's. So this vector of W will be found via optimization problem, but the main idea is to fit it to our observation. So instead of heights, we'll have a whole matrix of our clients and their features. So this will be our observations, and we'll actually find out these weights W via a procedure very close to maximal likelihood estimation. Okay, so how is it done? We came up to a conclusion that in logistic regression we model P plus, or a probability that the class equals to +1 if we have so conditioned on the vector of x's, our features. So this will be parameterized by vector W. And here we model, in logistic regression, we model it with sigmoid of W transposed x. Okay, errors here, but I'll be omitting this. Okay, so we'll start from here. So that means that P minus is estimated as 1 minus P plus. So 1 minus the sigmoid. After some transformations, this will be sigmoid of minus W transposed x. Okay, and so that's why we stick to y's as +1s and -1s. So these two expressions can be tricky and a bit cleverly grouped just in one expression. So the probability that we observe yi for an object xy, so it will be parameterized by w's. This is going to be, according to logistic regression model, it's going to be sigmoid of yi W transposed xy. Okay, so if yi is positive, then we have the first equation. If yi is -1, then we have a second expression. Okay, so this yi is either -1 for a negative object or +1 for a positive object. And in case it's +1, the first expression is valid, so it's for yi equals +1. And in case of yi equals -1, actually the second expression will hold. Well, so what we actually derived, it's a probability of observing a label yi for an object for an instance xy. So we have an instance xy, so a vector of features, and logistic regression actually models the probability of having label yi for this object. Okay, so in this case, an application of maximal likelihood estimation, MLE, will be to maximize the probability that we observe vector y of labels, given that we observe matrix X of instances and their features. Okay, so this will be parameterized by W, and we are going to maximize that. Okay, so why exactly this optimization task? The idea is that we observe data, and we'd like to maximize actually the probability that they are labeled as we observe. So in this process, we'll find nice values for W. So we see data, and we'd like to maximize the probability that we observe this vector of labels. So you see, it's pretty much the same as in estimating parameters of normal distribution when we observe some values of height. We'd like to describe our observations with some model. So actually a normal distribution of heights is only a model. It's imperfect. But we'd like to optimize the parameters of this normal distribution according to our data. And here as well, we are modeling, with logistic regression, we are modeling the probability of class +1. And we'd like to maximize exactly this probability that we observe these labels y given data x. Okay, so what it actually means, I'll continue from scratch. So maximum likelihood estimation will be maximizing this probability of vector y given data x. Okay, and we'll convert it to a product, a really big product, of the very same observations, so probabilities that label is equal to yi, given that we see a vector xy. And this product will be for E from 1 to L, where L is the number of instances. So we have matrix X. It has L rows and D columns, D features, and we have also vector Y of labels. Okay, so it's a very non-trivial task. So why we came from this probability to this big product? So here we make a really very fundamental assumption that our observations are independent. So most simple machine learning models make an assumption that our data is IID, that means independently and identically distributed observations. So first independent, and second identically distributed. Okay, so actually from here we just need only one assumption, that it's independent, and if these are random variables, so having a label yi given xy, so this will be a random variable, and we just assume that that we see pairs, let's say x1 and y, x1 and another pair x2 and y2. We just suppose that these observations are independent, so observing y1 for instance x1 is totally independent from observing y2 for vector x2. So these are independent. And for independent random variables, we can actually apply a probability product rule. And so in this case, observing the whole vector y will factorize into this big product of probabilities for each particular instance. Okay. And further, so here we apply our model. So this equality sign, I'll bring it here. So here is where logistic regression comes in. So we, according to logistic regression, we model this probability as we've seen, as sigmoid over the sigmoid of yi w transposed xy. And this big product is from 1 to L. Okay. So we are going to maximize this likelihood. So we convert it to a maximization problem. So we are going to maximize these with a vector of w. So choosing different vectors of w, we'll have different expressions for that, and we are going to maximize that. Okay, but it turns out that it's not really convenient to maximize a big product. It's much better to maximize a big sum. It's much more convenient. There are optimization reasons for that. And we'll be actually maximizing logarithm of the very same probability, py. Okay, so I see that. Okay, my head doesn't allow me to write it really beautifully. Okay, so again, I'll start from scratch. So instead of maximizing p of observing vector of y's for data x, it's a whole matrix, from this we'll go to, from this maximization task, we'll go for the task of maximizing its logarithm. So actually it's not really obvious why it's the same, but the idea is that logarithm is a monotonic function, and maximum of the first function wouldn't change if we just apply a monotonic function. Okay, so we'll actually be solving this maximization function with logarithm, and if we've seen that this probability is a big product E from 1 to L of some expression, so this will convert to maximization of some big sum of some logarithms. Okay, at this point we need a simple properties of logarithm function. Okay, so a small detour logarithms. Okay, it will be here on the right. Logarithm. Okay, so to begin with, what's a logarithm? It will be really quickly, just a very quick detour. So if 2 to the power of some value 4 equals 16, so from here we get 4 is actually logarithm of 16 with a base 2. And if actually I can give you a link, or you just Google logarithms, you'll be really very quick about that. So if e to the power of some x is equal to y, then x is actually a logarithm of y. And just ln means logarithm with base e. So how it works, from here we take a look at the base of logarithm. If we exponentiate it with actually the value of expression 4, we'll get this value 16. And by the same token, so here x is logarithm with base e of y, so this base e to the power of x equals y. Okay, and some properties. Logarithm of multiplication a and b is equal to log a plus log b. Actually, we can take logarithm of only a non-negative value. So to be precise, we need a modulus. We need an absolute sign here. Okay, and from this property, we can get that logarithm of a big multiplication of some x's, xy, multiplied by x2, and so on and so on. If we have L elements like this, so this big multiplication will turn into a big sum of logarithms of x, y. Okay, and so our optimization problem will be maximizing the sum of logarithms of this expression that we already derived. We've seen that it's a probability of having label yi given vector xy. This is going to be this sigmoid of this expression. And this is a big sum from 1 to L. And so we are maximizing this expression. It turns out that this argument of sigmoid is a very particular expression. It has some really interesting properties. So let's switch to here. The very same expression, sigmoid of yi double transposed xy. So you see, if we've seen that double transposed xy is actually a signed distance from a point to a hyperplane, and if we multiply it by its label, then we'll get something called margin. So an expression m capital of an instance xy is actually this product of a label multiplied by the distance to a hyperplane. The idea is really simple. So the very same derivation of a distance from a point to a hyperplane. So if we multiply it by a label, you see what we get here. It's going to be some estimation of how model is confident in its prediction. So let's take a look at these 4 variants. If x1 is a negative example, so it has a label -1, but the distance is positive, so double transposed x is positive here. We multiply this label y1 that is equal to -1. We multiply it by the distance that is positive, and we get a negative value. And so actually, if our model classifies that everything above the line is positive and everything below the line is negative, then we make a mistake. So we classified this object incorrectly, and moreover, the value of this margin is really high. Okay, I'll also draw this. The idea of margin is very important in machine learning. So let's take a look at it. Okay, so we separate the space by a hyperplane, double transposed x equals 0, and here we predict plus, and in this semi-space we predict minus. Okay, and let's take a look at several possibilities. So we take a look how we classify instances from our training set. And the first point, A, let's say that it's negative. So let's draw it as a minus, and its label y1 equals -1. But the distance to the hyperplane is positive. This rho 1 is positive. And a margin, so a margin is an expression yi multiplied by w transposed xy. So for this object, this margin is going to be negative. So if we take a look at the sign of a margin, so if it's negative, we make a mistake. So the classification is incorrect. And if margin is positive, that means that the sign of the label and the sign of distance coincide. So we've got positive margin. That means that the classification is correct. And here we dealt only with the sign of this expression, but actually its absolute value characterizes the confidence in prediction. So if absolute value of this margin, I would say, much bigger than 1, then the model is confident in its predictions. And if absolute value of margin, I would say, okay, let's say it's much less than 1, then it's non-confident. Okay, so for this point A, for this instance, we are confident in our prediction. So let's say it's far away from a hyperplane, but we make a mistake. So it's actually the worst case. So we are making a mistake, but we are very confident in our predictions. Let's take a second point, B. It's going to be a positive example. So label y2 equals +1, and it's also far away from hyperplane. So this object, this instance will be classified very confidently and correctly. So it's the best case actually. But what if we have some objects close to I'm confusing objects and instances. So instances, what if we have two instances very close to hyperplane, 1 and 2? We can say that the model is very non-confident in these predictions, and again it depends on the value of margin whether the model finally classified them correctly or not. So let's say if the third point is actually a positive example, so here we don't make a mistake, but if the fourth point is also a positive example, we've made a mistake, but not as big as for the first point where classification was confident but incorrect. Okay, and we see that actually this margin appears in this expression. So we'll be maximizing log. So this big sum of logarithms, sigmoid of margins. Okay, and only a final step to see how our optimization task will be looking, which form it will have. So for now we came to this conclusion that we are maximizing logarithm of sigmoids of margins, yi, w transposed xy. And this is a really big sum from 1 to the length of our dataset. So we'll be maximizing this by w, and the final step is only to simplify the expression logarithm of sigmoid of some function. So it's going to be logarithm of 1 over 1 plus e to the power of minus z, and so on and so on. So it's going to be logarithm of 1 plus e to the minus of z. Okay, so this expression will be a big sum of logarithm actually of 1 plus e to the minus of margin yi w transposed xy. Cool. So this will be a maximization task. Sorry, I lost a minus here. So in this expression there shall be minus right here. So this one I lost. So in this expression we'll have a minus here as well. And be careful, I'm changing a maximization task in a minimization. So I'm deleting this minus, this red minus here. It disappears, but we convert a maximization task into a minimization. So this expression will be, sorry, this expression is going to be minimized. Okay, so we started with the principle of maximum likelihood estimation, and we actually need to solve this minimization task. Okay, at this point we need some techniques for minimization. So we'll cover gradient descent in 2 weeks, speaking about regression task. So for now, let's think that we just have some optimization procedure, and that's how we get to this weights W. So we started from MLE principle, maximum likelihood estimation, and from here we got to this optimization task. And actually we'll start with some random initial values of vector W. So just some random numbers. And via this procedure, via minimization of this expression, we'll eventually come up to some really nice values of W star. We'll cover details in 2 weeks, so how actually it's done, what's going under the hood. But actually we're solving this minimization task. Okay, and final intuition about that is that here we've got margin. So we've seen that if margin is negative, then we've made a mistake. We classified an instance from a training set incorrectly. So a popular metric, so how many mistakes we've done with classification, actually the number of mistakes or incorrect classifications. So this number will be given really simply. So we'll calculate the number of cases where our label for an instance I doesn't agree with our prediction. Okay, so what we want from our algorithm is that its predictions, its answers match real values, real labels on the train set. If we calculate proportion of that, so we divide over L, this will be the proportion of incorrect predictions. And actually it's for a linear classifier, it's pretty much the same as the number of cases where margin for an object xy is negative. And here square brackets is just an indicator, so it's 1 if this condition holds and 0 otherwise. Okay, so if margin is negative, then we've made a mistake, and so this expression will be called 0,1 loss. It's actually just a fraction of mistakes that our algorithm made on a training set. Okay, let's just take a look how it differs from this expression, which is called logistic loss. So what we see here we'll call logistic loss. So how it differs from 0,1 loss? For only one instance, xy, yi, I'll write that logistic loss, or just log loss, for xy and yi is equal to that expression logarithm of 1 plus e to the minus of margin yi w transposed xy. Okay, so be careful here, it's only for y's from -1 and +1. Another really popular case is when the values for yi are 0 and +1, the expression will be a bit different. Okay, and let's plot this function as an argument of margin. So this product is margin m. Let's put it here. So margin will be on x-axis. So in this case, an instance xy yi will be classified correctly if margin is positive and incorrectly if it's negative. So I can plot a really very simple graph. It will be 0-1 loss. So eventually we'll try to build an algorithm which minimizes the number of incorrect predictions. And so here it's if margin is negative, so here on this side it will be 1, this loss, and here it's positive when we don't make any mistake. So it turns out we can't directly efficiently minimize the number of mistakes, because we've got these very not nice, okay, not, how is it called? Okay, I'm a bit struggling with a term for that, but here we have left-sided limit of this function being equal to +1 and right-sided limit of this function being equal to 0, and it's really not good. So a derivative here will turn into infinity. Okay, so or either it's not going to exist. Well, in this case, I'm not going to be really strict with that. Either it doesn't exist or it's infinite. It only, for optimization task, it means that we actually can't directly minimize this expression, so the number of mistakes. So instead, with logistic regression, we introduced some upper bound for that function. So if we plot this log loss, so it's going to be logarithm of 1 plus e to the minus of m margin. So the graph for this function will look like this. So actually it will cross this point only in case of log 2 when the base is 2, but actually the base doesn't mean pretty much. By default, if you see just logarithm and with no base, it means that base is equal to e. But here, if we take base 2, this will be the very same graph, but so it's actually an upper bound for 0-1 loss. So this blue one is 0-1 loss and red one is log loss. So it's really a very nice intuition about logistic loss. So it's an upper bound for number of mistakes, but we can directly minimize it with gradient descent. So actually we can calculate derivatives of this function because it's smooth and differentiable. And so we can directly minimize log loss. And this will be an upper bound for number of mistakes. So we hope that by minimizing log loss, our algorithm will be doing less mistakes and less incorrect predictions. So actually that's the intuition behind log loss. And further we'll come to gradient boosting. So gradient boosting will be able to minimize any loss if it's only differentiable. So if we have something like this, some other loss, With gradient boosting, we'll only require that it's differentiable, and then we'll have a specific procedure to minimize this loss as well. But logistic loss is very cool, so it's pretty simple. It has some nice theoretical foundations, and sorry, yeah, and we've seen that. So further, we'll see that we can minimize it efficiently with gradient descent or other optimization procedures that require a function to be differentiable. And more to that, logistic regression is very well studied, and it's known that predicted probabilities given by logistic regression in some sense behave very nicely. They are well calibrated, and there are other mathematical foundations for these being really nice probabilities. And so it turns out that logistic regression is applied very often. So as a consequence, mostly data scientists stick to logistic regression. So about 90%, according to Kegel's survey, use logistic regression. But we will discuss practical advantages and disadvantages in the second part of the lecture. Here we'll just say that these are crucial mathematical foundations for logistic regression, and I hope I delivered some intuition behind that. For those interested, I would really encourage you to dive deeper into theoretical foundations. So actually, this logistic loss is a special case of cross-entropy loss, and it's derived from KL divergence between the real data and the modeled probabilities. Okay, so I'm not actually delving into this. I would only say that there is some really nice I would say speculation that we have some distribution of our observations, let's say something like that. So these are our real data, a distribution of our training set, or in our case, just distribution of the labels. And we try to model it. We try to build some function that will be looking really similar. So these are our predicted distribution. In case of logistic regression, we dealt with probabilities, so the distribution of labels given features. Okay, and so actually we can compare these two distributions. So just you can think of point-wise comparison between distributions. So we can see that here they differ. We can calculate how much they differ. But KL divergence is the most popular way to compare two distributions. So it's Kullback Leibler divergence. Okay, sorry, I'm not sure whether I spelled it right. So KL divergence in this case will characterize how much our predictions differ from data distribution. And from KL divergence we can go to cross-entropy loss, and log loss is actually just a particular case. Okay, so here I motivate you to go, let's say, for deep learning book by Goodfellow, Benjo, and Curville. And part 1 is about math and machine learning basics, so it's a really nice source. And part 5 here in chapter 1 is about machine learning basics. So you can read here about the interconnection of KL divergence, cross-entropy, and log loss. So just to know something more about logistic regression and log loss, and to understand this theoretical basis. So for those who like theory, like understanding what are theoretical foundations behind algorithms, that is really very nice. Okay, and so in the second part, let's continue with logistic regression, we'll write some code and we'll describe its advantages and disadvantages, and we'll dive into competition where logistic regression is really very nice algorithm to apply.